Welcome to Homework Lib.
So, following problem, we're asked what is going to change if we're asked what is going to be the initial pH, meaning that we have added 0 milliliters of sodium hydroxide. And in order to solve this type of problem, what we need is first of all the pKa for the acetic acid, which is going to be equal to 4.76. Recall that this is going to be the substance that you're titrating over here. And at the initial conditions with 0 milliliters of sodium hydroxide added, what we're going to have is the following. We're going to have acetic acid, which I'm going to abbreviate as HAC, which is going to react with water in order to produce H3O plus the acetate minus ion. We're going to write down an ice table. Over here, we don't need the volume of the solution. We are only going to require the concentration, which is 0.100 molar. And initially, we're going to have 0 of hydrogen ion and 0 of the acetate. Let's say that we have a change of minus x, and plus x according to the stoichiometry of the reaction. Thus, at equilibrium, we would get 0.100 x and x. Our equilibrium constant, which is equivalent to the value for Ka, would be equal to the concentration of H3O plus times the concentration of acetate ion divided by the concentration of acetic acid. At the same time, we know that Ka is going to be equal to 10 to the minus pKa. Thus, Ka would be equal to 10 to the minus 4.76. Now we're going to replace the values of the equilibrium concentrations for each of them, finding x times x divided by 0.100 minus x. So over here we have two options. One is going to be to do the small x approximation, which, taking advantage on the fact that the equilibrium constant is going to be a very small value, what we're going to expect is that 0.100 is going to be much larger than the value for x. Thus, 0.1 minus x is approximately 0.100. We're going to first solve the problem like this, and then we're going to solve the full quadratic expression, and we're going to look at the differences. In this case, this small x approximation is going to be good whenever the value for x is lower or equal than 5% of the initial concentration of 0.100. This is going to be a threshold that we're going to employ. So now, under this approximation, our expression for Ka, which is 10 to the minus 4.76, becomes x squared divided by 0.100. Thus, x would be equal to the square root of 0.100 multiplied by 10 to the minus 4.76, giving us a value up to 3 significant digits of 1.32 times 10 to the minus 3. And what is this value of x? This value of x is the same as the equilibrium concentration of hydrogen ion. Thus, the pH, which is minus the logarithm of this concentration, would be equal to 2.88. And with that, it would be all. Over here, we can verify that the value for x is going to be much smaller than 0.100. So for example, over here, x is going to be equal to, as a percent, it would represent 1.32% of the initial concentration. Now, let's go ahead and try to solve the full quadratic expression just to see what is going to happen if we don't do the approximation. In that case, the value for Ka, let me separate over here, is going to be related to x squared, and over here we're going to pass 0.100 minus x. Which is going to give us the expression 10 to the minus 5.76 minus 10 to the minus 4.76 x is equal to x squared. Thus, x squared plus 10 to the minus 4.76 on x minus 10 to the minus 5.76 is going to be equal to 0, which, upon solving either on your scientific calculator or employing the general quadratic formula, minus b plus minus square root of b squared minus 4 times ac divided by 2a, you're going to arrive to the two results. One is going to be negative, which is going to have no physical meaning, and the other one is going to be positive, which corresponds to 0.0013096. Notice that this value is going to be very close, up to 3 significant digits, with the one that we found with the approximation. Just to verify what is going to be the difference on pH if we do the approximation, and if we not, the value for x2 is going to be the concentration of H2O plus, as we were mentioning before, 1.3096 times 10 to the minus 3, and thus the pH, which is the minus logarithm of this quantity, would be equal to 2.883 in this case. So essentially, the pH up to 3 significant digits is going to have no change, and it is going to stay as 2.88. So as you can see, the small x approximation is going to work well whenever we have a value for the equilibrium constant that is going to be small enough, meaning that the portion of x indeed is going to be much smaller than the initial concentration, and thus we can employ that to get the result without solving the quadratic expression. And with that, it would be all. Thanks and have a good one.